what we've got going on. So you guys took a quiz on Friday or Saturday. You submitted a homework on Thursday and a homework on Friday. I've graded one of those homeworks. The quiz is automatically graded. And we'll have another short quiz on Wednesday. So I just need to send out what the topics were. Could I just hear, what did you guys think of the quiz? Because the quiz was supposed to be kind of easy points. Like I gave you what the topics were and you had plenty of time. Did you guys feel like the quiz was hard or easy? Do you think it was fair or unfair?
I think the quiz is pretty easy, straightforward. It's not much of a thinking because it's just a. But one of the question got me into the thinking was the 1,000 and the 5,000. It almost tricked me to choose the wrong one. Almost.
Okay. Yeah. So some of them I think are, yeah, they have good decoys, but it was okay. Maybe the wording was tricky. Okay. Sorry about that. What, like, which
I
one
know
was?
which one. It was the first question for me. And the problem was that computer science, it was like the use of computer science in economics or application of mathematics and statistical methods, which are both in the definition, but the keyword was application. And like that made me sit there and think for forever which
Yeah.
one to choose.
Okay. I'm sorry about that. I was totally trying. So what I'm trying, it is a hard thing to do to make a quiz that's not totally obvious, but also totally fair. So it's like, it's hard to do like, so I'm sorry about that. I will try to make them less, I will try to make them as straightforward as I can. So I'm sorry about that. I didn't mean to trick you. Let me see, I've got a couple chats. Same, the wording was tricky. Hey, professor, I heard you call my name, but why, if I was like, okay, someone who puts others over themselves and sacrifice for the good of others. That's great. I just got my grade back for assignment 1 and it looks like the file didn't work. If that is you, feel free to upload it again. I know this homework, I downloaded a whole zip file and so I had files and files and files and files and I went through every.
It's because I did it on Notability, so maybe something happened, or maybe I had something else that was called assignment 1.
Okay.
On my
So
computer.
why don't, could you email me privately and we can figure something
Yes.
out? I'm not sure what the best thing is to do here.
Okay.
But yeah, let me know. Okay. So then we're going to try to get through lectures 5, 7, and 8 this week. And we're not going to do lecture 6. Lecture 6 is all it's about is what happens if you ignore the constant term in a regression. And we never do it, and it's not that important. And so it will not be tested. Lecture 6 will not be tested. And it's very unimportant in my opinion. So let's go. Let me show you a piece of research that I thought was super interesting. So this is, let me share my screen really quick here. Oopsie. So this is a figure made by a good friend of mine who just graduated from Berkeley. And so one of the really challenging things in the last couple of years has been to try to figure out what role policing has on the safety of American citizens. And so this is a really interesting figure. The red line is the deaths of Black motorists as a fraction of what they were in 2015. So you can see if you look in that's average pre-2015. Oh, the average of pre-2015. Okay, so you can see that they're both kind of hovering around 1 because they're because these are averages. And so the blue line is white motorist deaths, and the red line is black motorist deaths in Missouri. So the reason Missouri is important is because of Ferguson. So Ferguson happened in 2014, and police were induced in various ways to pull back from policing black neighborhoods and black areas where there are lots of black motorists. And so the thing that leaps out is that over time, being a black motorist becomes more and more dangerous. So by 2020, the increase in black motorist deaths is 40% above what it is for white motorist deaths when they began at the very same level and the very same trend. You can see that these are kind of two lines that move together until about 2014, 2015. So it's just a really interesting piece of the collage of evidence about what it is that cops do for people. So a 40% increase in motorist deaths is just kind of amazing. So we'd call this a difference in difference. I think we get to this after the midterm, and it's basically, we have two series, and one of those series is treated at some point in the window of our data. So here we have a treatment that's basically black areas are going to be less policed starting in 2014, 2015, and white areas are going to basically be policed the same because there aren't strong penalties on having bad interactions with white motorists. And so there's a difference in difference. The black neighborhoods are treated at a discrete point in time, and white motorists are sort of always untreated. So it's a nice kind of quasi-experimental design. Any questions about that? Okay, let's go back to lesson 5. Let's see if we've got lesson 5 handy. Okay, so questions from last week, anywhere last week. We were talking about how the units that we use to measure things affect how we interpret our regression. So that's where we're going to pick up today. And okay. Let's see here. I've got my stylus back, so hopefully my writing will improve. One thing that I botched on Thursday when we were together was I was trying to prove that the new beta knot is going to be the same as the old beta knot. So I'm sorry, let me back up one slide. So say what we're thinking about is, what if we multiply an x variable by some constant? So say first we have that beta 1 is the relationship between x, the covariance between x and y divided by the variance of x. That will give us our beta 1, which we derived earlier. The question is, what if we wanted to know what a new beta 1 will be? Sorry, I'm going to put a little star up here. If we multiply x by a constant. So say we by constant, and we'll call our constant a. So say we had the x was how tall you are in feet. Where the units are in feet. We could multiply x by a constant called 12. If we multiply your height in feet by a constant 12, instead of measuring your height in feet, we'll measure it instead in inches. And so what will the new beta 1 be if instead we're using as an x our height in inches rather than in feet? And so first we went through the work, and we learned that the new beta 1 will be 1 over beta, 1 over alpha times the new beta 1. I'm sorry, times the old. I'm so sorry, I'm already gobbled. So the new beta 1 will be 1 over alpha times the old beta 1. I can't remember if I said that correctly the first time around, but I don't think I did. So the new beta 1 over here is going to be equal to old beta 1 divided by our A. And we talked about how that's kind of intuitive because as you're making the A steeper, as you're making the X bigger, you got to make the beta less large. Or if you make the X smaller, you have to make the beta larger. So this is something I gummed up. I said the truth, but I missed a step. I couldn't explain how this 1 over A got in here. And the way that this 1 over A gets in here is that beta 1 star is equal to 1 over A times the old beta. So that's just this equation right here. Beta 1 star, the new beta, is equal to 1 over A times the old beta. So when we substitute in 1 over A times the old beta, that makes our life nice and simple because these A's cancel out. And so we're just left with the same formula for beta naught. So the new beta naught is identical to the old beta naught. So that's great. Okay, questions on that? This is something that's worth just kind of going through a couple times and getting your head around it.
What would the constant be? How would we find it?
The constant will usually be in the problem. So remember, even just up here, we were measuring. That's a really good question, actually. So that's a very good question. So here we have 2 ways of measuring sales. First, up here, we're measuring the sales in dollars. And here we're multiplying the sales in millions of dollars. Millions, okay? So the A here, what do you multiply 21 million by to get 21? And the A for this example would be 1 over a million. Okay. So
That makes sense.
all you'd have to do is divide this by this, and you'd get 1 over a million. Or I'm sorry, divide this by this and get 1 over a million.
Okay.
Very good question. Okay. So that's that. So this goes back to the example that we did just before on Thursday, before we did that little math. So remember, our company profits were in terms of dollars to begin with. And so they're a million times company profits in terms of millions of dollars. So the sales in terms of dollars is a million times the sales in terms of millions. Sales in terms of millions. So the new beta 1 is equal to 1 over a million times the old beta 1. And so that's why we get a beta of 30,000 in one of the examples and 3% in the other example, just based on whether the units of that of sales are in millions or in dollars. So in words, finding that a CEO makes 3 cents for every dollar the company earns in profits is equivalent to saying that a CEO makes 300,000 for every $1 million the company makes. In either case, when profits are 0, the CEO salary is 400K. and you would see that in both of these examples in the equation that you get, that it's 400K, whether they at when profits are zero. Okay. Let me stop there. This is just it can be tricky to get your head around, but it's kind of a really important thing to just think through and make sure that I've said it right. And yeah, let me just take questions. I'm sure there must be some. Let's see who we've got. Ibrahim, Katrina, Kimberly, Leanna, Levi, Luis, Manuel, Ned. Makes sense. Oh, guys. Okay. Sounds good. Awesome. Okay. Okay, so we can also change the scaling of the outcome variable. Suppose that we estimate the dollars spent on housing in Santa Cruz County as a function of the prime loan interest rate. So we could have the dollars spent in housing right here as a function of the interest rate. And we've got here, how much spending is there on housing? We've got $150 million minus $20 million times the interest rate. So say the interest rate were, 1% or whatever, we would find that the spending on housing in Santa Cruz was 150 mil minus 20 mil times 1. So that would be 130 mil. Okay. So now we could divide Santa Cruz housing by $1 million. I know that a lot of you want to have rental properties, so that it's all in terms of millions of dollars, and we could rerun the regression. So here, it's the exact same regression actually, except for here, the spending on SE housing is in millions. For here, it's in dollars. Okay. And so what happens? Well, this is kind of cool. This is a great example, actually. So the beta naught shrinks by it shrinks by 1 million. So it goes from 150 million to 150. And the coefficient on interest rate also is divided by 1 million, from 20 million to 20. So how do we interpret the coefficients of this new specification? It's actually basically the same, that the amount of spending on housing in Santa Cruz is 150 million minus 20 million times the interest rate. Okay, so this is kind of fun. So first, we're gonna this should look like home. This is something we've seen a few times. And then the question is, what is the beta 1 star and the beta naught star when we use y times a constant instead of y? Okay. So we're going to do the same kind of math that we did in a little bit ago, and we're just going to put in y to our beta calculation. So remember, beta is the covariance between X and Y, where now our new Y is Y times A divided by the variance of X. Okay. And what can we do? We can pull this A out. This is one of the properties of our covariance that we learned a couple slide decks ago. And then what we can notice is that this is the formula for our original beta. And so A times covariance of X and Y over the variance of X is actually the same as A times our original beta. Sorry. So this becomes beta, and the A stays A. Okay. So what is that? What did we learn? We learned that the new beta 1 star, the star just means it's the new guy on the block, is equal to the old beta times A times alpha. So if we multiply Y by 1,000,000, the new beta will be 1,000,000 times the old beta. If we multiply Y by 1/1000, the new beta will be 1/1000 times the old beta. Okay, so any questions on that? So I'll just scoot down a little bit and do beta naught. Got beta naught here. And remember, beta naught has a function. We're just going to use the function for beta naught, but we're going to notice that our Y bar, that is the average of Y, will be the average of Y times A. And then we're going to do what we did in the last one, I suspect. Yep. And we're going to notice that we have a formula for the new beta that we can use. So the new beta is equal to the old beta times A. So that's where this guy is coming from. Let me just use a highlighter. So this will become this. Okay. And then this A times Y bar, you can take out the Y and the A, because the A is just going to multiply by the average. So we don't need the bar over the A. Okay. And then what we can see here is we've got a common factor. We've got a Y in front of an A in front of Y bar, and we've got an A in front of beta 1 times X bar. So we can factorize out that A, and notice that this is the formula for our original beta naught hat. So original beta naught hat becomes this, and our A just comes right over. So when we are looking around and we want to know how is our new beta naught related to our old beta naught, what we'll find is that new beta naught is equal to A times the old beta naught. Okay, so if we multiply our Y by 1,000,000, our new Y-intercept will be 1,000,000 times the old Y-intercept. If we multiply the Y by 1/10, the new intercept will be 1/10 of what the original intercept was. So in words, when the outcome Y is scaled up or down, both the slope coefficient and the intercept are scaled by the exact same amount. So that's kind of intuitive. If we're spreading out or shrinking down the X in the data, everything is just going to have to change proportionally, the Y-intercept as well as the slope. Okay. I'm just going to take a little break. I've got to go eat something because I'm getting lightheaded. I'll be right back. Sorry about my bad blood sugar. Not bad. So here we've got two things. So this isn't that deep, but it's just kind of it just kind of is important about how we interpret the results. So for instance, like say that you didn't know what this was. You didn't know that this was in millions and this was in dollars. You could get very different ideas if you thought that this was in millions up here. And so every time the interest rate went up by 1 point, it would go down by 20 million, for instance. So that if you didn't understand what the units were in the y variable, you would really easily be mistaken about something. And you wouldn't be mistaken by a little bit, you'd be mistaken by several orders of magnitude, six orders of magnitude. So it would just be kind of fundamental, but I mean, I think it's all intuitive. So Santa Cruz housing in terms of dollars is a million times Santa Cruz in terms of millions of dollars, and therefore we're going to get something very different in terms of beta naught and beta 1 when we use either. Okay, so this is a really good example. Total change in subjects. We're not scaling right now. We're not changing the scale of our y or our x variable right now. We have the number of crimes in a place, in a city, and we have the number of police in a city. So this is a kind of a classic question in criminology and later in economics. So say we've got New York has 400,000 crimes and 35,000 police officers. Santa Cruz has 980 crimes and 100 police officers, et cetera. And we're going to estimate a relationship between the number of crimes and the number of police. And what we get is actually that the more police you have, the more crime you have. So for every additional cop that there is in a city, we find that there are actually 12 additional crimes. So it's as if every policeman is producing crime. Why are we getting that police and crime are positively correlated? What do you guys think?
Because if you have a lot of crime in your town, you hire more police officers.
Okay, so that's true. That's a very good point. You could hire police in response to crime. Okay, yeah, okay, so that's a very good point. We are actually dealing with a problem a little bit simpler than the one that you've identified, which is totally and 100% correct. If there's no crime in a place, you don't hire any police. And if you're living in New York in 2020, you're like, where are the police? We need more. So the places actually that were, what's really interesting is in all the defund the police stuff last year, when they surveyed people and they asked whites and blacks and Asians and Hispanics whether they wanted the same number of police, more police, or fewer police in their area, blacks were actually the most likely to say that they wanted their police maintained or increased. They had the smallest fraction of people, fewer than 20% of people saying that they wanted fewer police in their neighborhoods. And it was, kind of rich white people that had them, wanted less police. And of course, because they're less exposed to crime than blacks and Hispanics. Okay, so this is actually a bit of a simpler issue, which is that New York is an enormous metropolis, and Meadville is a tiny town that you haven't heard of. And so a place with many, many more people will both have more crimes and more police. So one of the simple ways that we essentially control for it or deal with that is basically to say, we'll divide the number of crimes by the number of people in the city, and we'll divide the number of police by the number of people in the city. So instead of the number of crimes, the count, we'll use the crime rate. Instead of the police, we'll use the police, basically the police rate, which is just a fraction. What fraction of the population are police, or how many police are there per 1,000 citizens? Okay, sorry. So let's go down. So how many crimes do we predict for a town with 100 residents and 1 police officer? Oh, this is a great way of kind of seeing the same thing. So say we had 100 residents and 1 police officer, how many crimes would there be? There would be 256 plus 12 times 1. And then there isn't a coefficient for residents. So it's as if we're saying plus 0 times 1,000 residents or whatever it is. We don't have a coefficient for residents in the model. And so we'll get something like 256 plus 12, 8, 6. Did I do it wrong? No, 2. So 200. We predict 286 crimes in a town with 1,000 residents and 1 cop. How many crimes do we predict in a town of 100,000 people and 10 police officers? So we'll get 200. Why? Oh, my stylus. 256 plus 12 times 10 police officers. Remember, we don't have a coefficient for 100,000 residents, so we can't enter it into our model. We're going to get 256 plus 120, which will be 673. Do these answers make sense? They make sense in a way, but not really, because this place with 100,000 people should have about 100 times more crime than a place with 1,000 people, because it's 100 times larger. So the fact that their crime rates are their number of the predicted crime in these 2 places is so similar is actually like obviously false, because a town with 100 times more people should have probably 100 times more crime, or around 100 times more crime. So no, crime should be about proportional to the population. Sorry, to the population. Okay. Questions there? Let me just pause, see if I can help with anything. Neb, Noah, Saul, Stephanie, Warren, Yesenia, any questions here? Okay. So what do we do about this? We usually use rates. So problem is the number of counts of crime is not actually, is basically going to have, we're going to have a problem where we're not controlling for how big a city is if we're using the number of crimes and the number of police rather than how common crime is among people, rather than how many crimes there are in a city that you could count. So a big city like New York will have maybe hundreds of thousands of crimes, but a given person in the city might never experience crime, might never be a victim of crime in a year, because crime is actually pretty uncommon. Okay. So what we often do is we divide a count like crime by the relevant population size. And what that does is it converts the variable into a rate. What was a count will now be a rate. So we've all heard of crime rates. The crime rate is going up. That's a much more sensible statistic. How many murders are there per 100,000 people? How many aggravated assaults are there per 100,000 people? Rather than how many crimes are there in a city. It's not that useful of a statistic. If a city is just getting larger over time, it will appear that the crime will grow, but that's not really the item that most people are interested in. They want to know, what's the risk of being murdered? What's the risk of being assaulted? What's the risk of being raped? So if we divide the number of crimes by the number of police by the number of people in the city, usually in thousands or 100, and I think the murder rate depends on when you're doing it, but in cities, it will be the number of murders per thousand or something like that. Our new regression might be crimes per thousand is a function of police per thousand. So how many policemen or women are hired in a city per thousand citizens. So this will likely produce more reasonable estimates. So we have crimes per thousand is 12.4 minus 3.2 times police per thousand. So for every additional police you hire per thousand citizens, the crime rate goes down by 3.2 crimes per thousand. And that like when we do, there's a really cool paper, and they used Argentina. And basically what happened in Argentina, there were these terrible terrorist bombings of synagogues. And so what the government did is they put a police officer on every block where a synagogue was located. And then the economists measured how much crime fell on those blocks where a cop could see. What they found is like crime fell within like a 1 radius block of where the cops are, and didn't fall elsewhere. And so it's just kind of a really nice kind of experimental evidence that the cop is basically reducing the crime in his or her immediate vicinity. Okay, so how many crimes do we predict in a town of 1,000 residents and 1 police officer? Okay, so how many crimes? Okay, so if we did this, we get how many police per 1,000 is 1. Oops. Police per 1,000 is 1. So we're going to get 12.4 minus 3.2 times 1. So that's going to be 9.2 crimes per 1,000. And it says, it doesn't say what's the crime rate. It says how many crimes do we predict. So we have 9.2 times 1,000. And so the number of crimes there, because there are 1,000 residents, would actually be the same. It will be 9.2 crimes in total. How many crimes do we predict in a town of 100,000 people and 10 police officers? So the police per 1,000 will be actually smaller. So it will be 0.1 police per 1,000. So we're going to have 12.4 minus 0.1 times 3.2. So this math gets kind of annoying, but it's 12.4 minus 0.32 now. So it's going to be something like 12.08 crimes per million, per 1,000, I'm sorry. So how many crimes do we predict? Here, there's 12.8 per 1,000, and there are 100,000 people. So we're going to get something like 12,000 crimes, 12,080 crimes. Okay, in this bigger city. So do these make sense that we have 9 crimes in a small town of 1,000 people and 12,000 crimes in a town of 100,000 people, yeah, that makes much more sense. That's 12,000 is very similar to 100 times 9.2. They're not the same, but they're in the same ballpark. So there's the crime rate won't be that different. So these answers make sense. I'd say yes. Crimes are proportional to the population. Okay. Let me stop and take questions. Let's see, Cameron, Derek, Devin, Esmeralda, Ibrahim, Kimberly, Katrina.
Professor,
Yes.
when you go from the 12.08 to the 12,080, how did you get? Did you multiply by?
That's a great question. So what I did was so basically what I know is that there are 12 crimes per 1,000 people in this town, or that's what's predicted. So let me just put this in blue. So how many thousands of people are in this town? It's 100,000 divided by 1,000. So I'm going to cancel out 3 zeros on the bottom, 3 zeros on the top. And I learned that there are 100,000 of people in the town. And so, wait, did I do something wrong? So I might have done something wrong, but so what we get is, I'm sorry, I did something wrong. Thank you, Ibrahim, I appreciate it. But so basically what I'm doing is I'm just multiplying this by 100 to get how many total crimes there are in the city, because 12 is the number of crimes there are per thousands of people. So you get the total number of crimes. We multiply this by how many thousands of people there are. So it's 12.08 times 100 thousands of people. And that gives us 1,200. I apologize. That's my mistake.
So I have a quick question. So for the one that's right above that, the one with the 9,000, I mean the 9.2. So that one you just multiply by 1,000? I mean,
Exactly. I just multiplied it by 1 over because there are just 1,000 residents. So the number of crimes in that town are exactly the same as their crimes per 1,000 people.
I mean like because the one below that you take 100,000, you divide by 1,000. So that's why on the top you just take 1,000 divided by 1,000 and then you get 1.
Exactly.
Oh,
That's exactly right. So I should have done this explicitly, but to find out how many thousands of people there are, we just are going to divide the number of residents by 1,000, and we're going to get 1. And so when we're taking the crime rate and trying to make it into, convert it into the number of total crimes there were in that town, we're just going to take the crime rate and multiply it by 1. So that's just itself.
So if I want to find like per 100 by, for example, I mean, I just have to take the number of residents, divide by 100 instead?
Exactly. Yep. And then you'll get 10.
All right. Okay.
Exactly. You got it. Great question. I'm very sorry that I skipped that step out. That makes it's probably very crucial. Let me clear this, and if there's another question, I'll have some space. Any other questions there? Okay. So we're going to change tracks again. A binary variable is a variable that's either 1 or 0. And we often use these to indicate characteristics where 1 means yes, that characteristic is true of the person, and 0 means no, that characteristic is not true of the person. So we might have a variable in the data called female that's 0 when the person is a male, and 1 when the person is a female, or 0 when the person is not of Hispanic origin, or 1 if the person is of Hispanic origin. Smoker would be 0 if the person is not a smoker, or 1 if the person satisfies the definition of smoker, whatever that would be. I think usually like they smoke 3 cigarettes a week or greater, or something like that. And then college graduate could be 0 if they haven't graduated from college, or 1 if they have. So these are just really nice, simple variables that describe whether or not a person in the data has a certain quality or characteristic. So how do these kind of, how do we interpret coefficients when these are either our explanatory variable or when they're our outcome variable? So they're really actually super simple to use. Suppose that we did a regression where we regressed wages on being a smoker. So we've got wages are equal to $18 in our regression, $18 minus $4 times smoker. So what this means is what's the predicted wage for a smoker? It's equal to 18 minus 4 times smoker equals 1. So that would be 14. What's the predicted wage for a non-smoker? It equals 18 minus 4 times smoker equals 0, not a smoker, which is 18. Okay. So the predicted earning, the average smoker is earning $14 an hour. The average non-smoker is earning $18 an hour. Typically, the coefficient on X is the effect of a 1 unit increase in X on the outcome Y. And it's the same with the binary variable. You're going from 0 to 1. So it's a 1 unit increase in the explanatory variable. And so the only difference is that it can't go above 1 or below 0. It's going from 0 to 1 and not going to 2 and not going to 1.5. It's just 0 and 1. So -4 is the quote unquote effect of being a smoker rather than being a non-smoker on your earnings. So it's not true that this is necessarily the effect. It might be that smokers have different education, that smokers have different experience, their ages are different. There could be a lot of reasons that smokers earn less other than that the smoking is causing them to earn less per hour. So questions on that? This is kind of, I think this is just like a really nice use of regressions. These are really clear, like easy variables. These never can be too complicated because they're only 0 or 1. Leanna, Kimberly, Levi, Luis, Manuel, Neb. All good? Okay, let's keep going. So this is another kind of, it's related, but just a slightly different thing but it's actually related to the binary variables. So a percentage point and a percent are different, and they're different in an important way. So the percentage point is the absolute change, and I'll give you an example of that. And the percent is the relative change. So say I got 1 inch taller, that would be, you know, something like 2% taller, but the percentage point would be like the inch, and the 2% taller would be the percent. So percent is relative to what I already am, and percentage point is the actual increase in the probability or the in my dumb example, in my height. So if the fraction of people who smoke increases from 20% of people to 30% of people, this is a 10 percentage point increase in smoking. How do we get that? All we do is we subtract 20% from 30%, and we find that it's a 10 percentage point increase. So that's the number of points different between 30% and 20%. The percent is slightly different. It's relative. So we have the exact same example where we've got smoking going from 20% of the population to 30%. What that is a 50% increase in smoking. How do we know that? We just find the difference between the two is 0.1, and we divide it by the base, which is 0.2, and that will give us 50%. So there's a 50% increase, but it's a 10 percentage point increase. So that is really just a really important. And then usually, if once you get lazy like me, you just do you don't do the subtraction. You just do 0.30 over 0.20 minus 1. So you would get, this would be 1.5, and you just subtract the 1 and you get 0.5. So let me give you another example. Let's try one more example here. So let's say we went from 1% of the country was watching Mandalorian to 2% of the country was watching Mandalorian. Mando, okay? So what is the percentage point increase in Mandalorian viewership? All we do is we take 0.02 minus 0.01, and we find that there is a 1 percentage point. So we'd say, if we were talking out loud, we'd say 1, and we sometimes write it this way, 1 percentage point increase. Okay, so maybe that doesn't sound that big to you, but it's actually quite big, because relatively, when we want to calculate the percent, it's going to be 0.02 minus 0.01, all divided by 0.01. That's 0.01 divided by 0.01. So what is that? That's a 100% increase in the fraction of the country that's watching Mandalorian. Okay, so you in general, when we write a paper, we will just say both of these percent. So I'll say there was a 1 percentage point increase in the viewership of Mandalorian, parentheses, 100% increase. Sorry, 100%. 100%. Okay. Does that make sense? Questions here? Noah, Saul, Stephanie, Warren, Yesenia. Thumbs up. Okay. Who did the thumbs up? It's not in chat, but it's in no questions. Gotcha. Okay. Yesenia. Cool. I didn't know you could do that. That's great. So we're going to study some linear probability models, which are measured in percentage point effects, and some natural logs, which are measured as percent effects. So sometimes we have an outcome variable y that's binary. It's either a 0 or a 1. And here the predicted value is a probability. So whenever the outcome variable is binary, the predicted value is a probability. Beta 1 is the percentage point change due to the explanatory variable. So here's a good example. Suppose that we wanted to regress whether or not someone graduates from college on their SAT scores. The variable graduate is 0 if the person didn't graduate in 6 years, perhaps, and did not graduate, and is equal to 1 if they did graduate in 6 years. That's for some reason how they measure it. It seems like they should be measuring 4-year graduation, but they measure 6-year graduation. So we've got graduate, and here graduate is a binary variable. So it equals 0 or 1, 1 if they graduated, 0 if they didn't. That's the baby. He's tired. That's his tired cry. Okay, so we're basically going to predict the likelihood of graduation based on your SAT score. And what we'll have is something like this. So we have the predicted value of your graduation is 24, 0.2, sorry, not 24, 0.24 plus 0.0005 times your SAT score. So how do we interpret 0.24? 0.24 is basically how likely would it be to graduate if somehow your SAT score is equal to 0. So in practice, we don't see SAT scores of 0. The minimum in each section is 400 points. So this is just a y-intercept. There's actually nobody at SAT equals 0, but it's just where we predict that your the graduation would be if SAT scores could be 0 based on the SAT scores that exist and the graduations that exist for them. What is the likelihood that a person with a 1,000 SAT score graduates from college? So all we'll do is plug this in, 0.24 plus 0.0005 times 1,000. So the way I do this is I go whoop, 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 and cancel this out. So what we get is 0.24 plus 0.5 is equal to 0.74. So someone with a 1,000 point SAT score has about a 74% chance of graduating. How much more likely is someone to graduate if he or she scores 100 points higher on the SAT? Okay, this is a great question. So we can go 0.24 plus 0.0005 times 1,100. And basically, what am I going to do this math? I'm going to notice that this is the same as 0.74 plus 100 times 0.0005. 0.05. So it's going to be 0.79. Is that what you guys get? Anyone else get that? So that's how likely they are to graduate, but it's not how much. So the question is actually, I answered the wrong question. How much more likely is someone to graduate if he or she scores 100 additional points on the SAT? So what that would actually be is if I wanted to just solve that question, I would multiply the beta 0.0005 times 100. Okay, and 0.005 times 100 is that they were 5 percentage points more likely to graduate. We could write that also in terms of percent. So that's 5 percentage points. Or we could calculate the percent increase by dividing 0.05 divided by 0.74. Anyone have a calculator? Let's see if I can. 0.74. So that's
0.0675 or
perfect.
6.
Yep, 0.0675. So we'd say that's about 7% greater. Okay. Questions here. This is like I would really want this would be a great thing to make sure we have totally clear. Awesome. Devin, thank you. Leanna, thank you. I appreciate it. Okay, so we are just running out of time in terms of I want to kind of get started on the next deck. And so there's a part of economics that uses the natural log to change their variables. And basically all that it does, I'm not going to have this on the exam. Just make a note to myself, no natural logs. Okay. The natural log basically makes things interpreted as percent increases rather than percentage points. And so I'm going to take that off of the exam because we just don't have the time for it. So that's all that's left in the rest of the slides is the natural log. And it's useful sometimes, but it's not a core feature of econometrics. And I just want to make sure that we're able to get through the next couple decks. Okay, any questions on this? Units, binary variables, scaling, the difference between percents and percentage points? Any questions? Okay, we probably got to have a little break though. No questions. Okay. I'm going to, oh, okay, awesome. Let me just share my screen. Do any of you like America's Got Talent clips? I don't know why, but I just cry every time. Here we go.
What do you call a crunch wrap with double the seasoned beef, a crunchy taco, and a large drink for just $5?
Whoa.
Done up.
My brother works at Taco Bell.
Hello.
So.
Hi, how are you? What's your name? Name's My interpreter.
What's your name?
Sarah.
Nice to meet you, Sarah.
Nice to meet you, Sarah.
Hi, Sarah.
So I think I've worked this out. So you're deaf?
Yes, I lost all my hearing when I was 18 years old.
Wow. And how old are you now?
29. So it's 10 years.
Wow. And Mandy, how did you lose your hearing, if you don't mind me asking?
I have a connective tissue disorder. So basically I got sick and my nerves deteriorated.
Mandy, I don't think you're going to need a translator for this. That's a long time. That was one of the most amazing things I've ever seen and heard. Honestly, I never think I'm going to be surprised or amazed by people, and then you turn up, and with, I mean, just you, but it was your voice, your tone, the song was beautiful. Congratulations, you were straight through to the live shows. And you know what? We found each other.
Yes. And you can tell this is a song. And when you listen, it's done.
Hey YouTube, thanks for watching. If you like this and you want to see a lot more, all you got to do is click right here to subscribe. This is amazing. I think I feel a little viral.
Howie. I just think people are amazing. Like the stuff that they overcome is just incredible. She can't hear and she can sound like that. It's amazing. Okay. And I love the song. The song, that's a great song. What does she say? The only thing in my way is me. There's a great body of work that finds that people that believe that are much more happy and successful. It's called locus of control. If you recognize that your world and your destiny is in your own hands and under your influence, you're a much happier person and much more successful. Okay, so we go from univariate regressions. We've been working on univariate regressions for the last little bit. So now we're doing multivariate. So multivariate just means multiple variables at the same time. So usually in the past we've had one variable on the left. We always only have one variable on the left. There's only one of those guys, only one. And so far we've had regression equations where we've got one variable on the right, only one. Okay, plus u. So what we're going to do now is we're going to go break into a world where we've got multiple betas, multiple x's on the right. Okay, what does it mean to have multiple x on the right? How do we interpret the regressions? Okay, and so multi just more than one. Variate is variables, so multivariable regression. And So the very first slide deck that we went through, we were talking about ceteris paribus, which is the Latin meaning everything else held constant or still. And we can actually make ceteris paribus part of our regressions. And so what we'll be doing is examining the effect of 1x on y while holding all else constant. And I'll try to say this a couple times, but I'm sometimes going to say effect, even though it's not explicitly a causal estimate. It just makes it a lot easier to talk about what we're instead of saying the association between x and y, to say the effect of x on y is just much simpler and more natural to say, even though I don't usually mean that it's actually causal or that it must be exactly the causal effect. Okay, so this is a little of the outline, but we actually will just jump right into it because it's easier to go through by seeing than by hearing about. And so here is a regression equation that we actually would often, as economists, we will often estimate. We're interested in understanding the effect of the relationship between wages and different variables. And here we've got two x's. We've got an x called education, and we've got an x2 called experience. And how do we interpret these betas is important. So the first beta here beta 1 is the change in wages associated with a 1-year increase in education. And there's a little bit more to that, but it's the change. What we already know is that it's the change in wages associated with a 1-year increase in education. What sign do we expect this to have? We expect beta 1 to be positive. Beta 2 is the change in wages associated with a 1-unit increase in experience or 1-year increase in experience. What sign do we expect that to have? We expect beta 2 to also be greater than 0. Okay, so they have a little bit of an additional, what's it called, interpretation that we'll get into in a moment. Okay, so they're a bit different when we have multiple variables going on at the same time. So y is the outcome variable, as we had before. X and x1 and x2 are both explanatory variables. So before we only had one explanatory variable at a time, but now we can have 2 or 3 or 1,000, we'll find. And like before, beta naught is just the intercept. So it's a little bit different actually in this case. It's what is the expected value of y when x1 is equal to 0 and x2 is equal to 0. So it used to be just when x1 is equal to 0, where would the data be in y? Here it's when both x1 and x2 are 0. Beta 1 is really where the fun starts. So beta 1 is the change in y with respect to a unit increase in x1 while holding x2 constant. So essentially what we're going to be able to do is find out what's the relationship between x1 and y while we hold x2 constant, or what we often say is while we are controlling for x2. So often when people are discussing research on Facebook or Twitter or in debates, they'll say, well, this is the correlation between, X and Y is blah. And then the other person will usually say, well, that doesn't account for blah, blah, blah. Income, that doesn't account for immigration status, that doesn't account for blah, something that they think is correlated with both the X's and the Y's. So when we are able to include an extra variable here, x2, beta 1 changes its interpretation slightly. It's the change in Y for a change in X1 while holding X2 fixed. And beta 2 is a change in Y for a unit change in X2 while holding X1 fixed. So they have a slightly different interpretation, which is that they're the change in Y for a change in their X, while controlling for changes that are going on in the other variables. Okay, so this is the initial example that we went to, which is we've got a regression equation here where we're trying to understand what shapes wages. We have education, we have experience, and what we have is that for a unit increase in education, if you were to have one more year of education, on average, your wage would go up by $1.50. And if your experience increased by 1 year, your wage would on average go up by 75 cents per year. So the regression suggests that by holding experience fixed, each year of education is associated with a $1.50 increase in your wages. So for instance, if two employees both have 5 years of experience, then we predict that the one with 11 years of education will earn $1.50 more than the one with 10 years of education. Okay. So for they both have the same level of experience. What is the relationship between education and wages among people that have the exact same level of experience? That's one of the reasons we've got this thing. Both people have 5 years of experience. It's a really intuitive way of seeing what the effect of one variable is on an outcome, is by looking among people that all have the same experience level, or among people that are all the same gender, or something like that. What's the relationship? So these regression results also suggests that holding education fixed, each year of experience increases your wages by 75 cents per hour. So for instance, say we had 2 employees and they both have 8 years of education. So we're going to look in the data. We find that 2 people have 8 years of education, but one has 4 years of experience and the other has 1 year of experience. And then we predict that the person with 4 years of experience will earn $2.25 more than the one with 1 year of experience. How do we get $2.25? All we're going to do is calculate the the years difference in experience. We get 4 minus 1 times 0.75. That'll be 3 times 75 cents. And that's going to be 150, 225. Okay. So let me stop here. Questions on any of that? Yesenia, Warren, Stephanie, Saul, Noah, Neb, Manuel. No questions. Okay. Sounds good. So this is probably hopefully intuitive, but and sometimes even things that I think are intuitive are not, because I've said something wrong, or sometimes it's just I've been doing this for a long time, so it feels like it makes sense to me. But okay, so let's do we're going to do one. Why don't we do this? We're going to do this one example, and then I'll let you go for today, and I'll hang back and take questions, and then we'll get right back at it tomorrow. But we're on pace. We're doing really well. We just need to finish this deck, and then Wednesday we'll finish deck 8, and then on Thursday we'll do a review. Yes. Okay. So we have an employee has 12 years of education and 10 of experience. What do we expect her wage to be, or his wage? So we get 10, 50, 150 plus 150 times 12 years of education plus 75 cents times 10 years of experience. So we're going to have 1050 plus. So the way I'm going to do this is I'm going to say 150 times 10 is $15 plus 2 times 150 is 3. So that's going to be $18 plus 75 cents times 10 is $7.50. So I get lazy here. $7.50, $11, $18, $36. Do you guys get 36? Anyone else get 36 or something close to it? Okay, awesome. So we're getting $36 is her hourly wage based on 10 years of experience and 12 years of education. So here's a good question. If she takes night classes for 2 years while she's going to work and gets an associate's degree, then what do we predict her new wage will be? So this can be tricky. And thanks, Leanna. I appreciate it. Esmeralda and Leanna, I appreciate you working it out with me. Basically her education is going to go up by 2 years. She's going to school for 2 years, 2 plus in education. And it says that she's going to school while she's working. So her experience is going to go up by 2 years as well. Okay. What do we predict her new wage to be? So we're going to add 2 times 150 in education plus 2 times 75 cents for her experience. That's $3 and 150. So it's going to be 450. Sorry. So I get something like her new wage is after she goes to school for 2 years is good. I got the same thing, $40.50 an hour. Well, that's pretty good. Cool. So that's what we get there. Any questions on anything that we've talked about today or anything else? Oopsie. Awesome. Okay. So class dismissed, and I will hang back and take questions.